This is question 4 for the OCR Depth in Physics paper. We're looking at the IV characteristic for a silicon diode. This is the graph that's been given to us with voltage along the x-axis and current along the y. The first question asks us to comment on the resistance at 3 distinct intervals from 0.6 to 0.65 volts, from 0.65 to 0.75, and then from 0.75 and above. The first thing to say is that the mark scheme for this question is not correct. This is the mark scheme for a different question because the voltage ranges that it talks about are different. They're 1.2 to 1.5 volts, so they're different regions, and you can see those voltages don't even exist on the graph. But nonetheless, let's see what we can do with this question. Let's look at those distinct regions that it's talking about first. That's from 0.6 to 0.65 there, and then from 0.65 to 0.75, and then there and beyond. State and justify how the resistance of the diode increases, remains the same, or decreases in each of these regions. The first thing to say is, how do we work out resistance? Resistance is voltage over current at a point on the graph. It's not the change in voltage over the change in current, and therefore it's not the gradient of this curve. It's just if you take a plot and take the voltage and current for that point, work out the resistance from there, that's what we're doing. So if we do that for the first region here, we'll find that we're dividing some value of voltage by 0 because the current is 0 there. That will give us an infinite resistance. So from 0.6 to 0.65 volts, resistance is infinite. Then we can note that the resistance starts to drop because if you work out the resistance at these points, they are not infinite. So the resistance has dropped or decreased to whatever the values are here. Because we're going from 0.65 to 0.75, we can take the resistance of this point here, which would be 0.75 divided by 20 times 10 to the minus 3. So let's do that. 0.65 to 0.75 volts. Making it nice and clear for the examiner to know which region I'm talking about here. Resistance decreases. And we can calculate the value of the resistance at that point. R equals V over I, and so that's 0.75 I said to 20 divided by 20 times 10 to the minus 3, giving us 37.5 ohms, or 38 ohms we could say. Decreases to 38 ohms at 0.75 volts. We're being nice and thorough and nice and clear here to indicate what the resistance specifically decreases to. Last region is 0.75 volts and above, or above 0.75 volts. What happens there? Well, the resistance continues to decrease, and we can say it decreases to a very low value, as indicated by the steepness of the graph here. I'm not looking at the gradient, but just appreciate that the steepness tells me that the amount of current, the current increases much more significantly compared to the voltage. So that's what I'll say for that. Resistance decreases to a very low value. Current increases significantly compared to voltage increase. There we go. The steep gradient indicates that. Okay, let's move on to part B. We're now given this selection of circuit diagrams, and we want to know which of these circuits would we use to get that IV characteristic for the diode. So one student uses this circuit, another student uses this circuit. Which one is, well, the question says only one of the circuits is suitable to carry out the task, so you've got to decide which one it is. and whichever one you choose, you've got to draw the LED, 100 ohm resistor and suitable meters to complete the circuit, to show how you use the circuit to work out the IV characteristic. And then the question further says, explain why only one of the circuits is suitable and why the 100 ohm resistor has been included. Let's start off by saying why the 100 ohm resistor is there. It's there to limit the current through the LED. It's there to protect the LED. So that's what we'll say starting off. The 100 ohm resistor protects the LED from burning out. Now I'm going to star that point there because that's one of the key points. These questions in the mark scheme are banded to different levels. So you have level 1, which can get you 1 or 2 marks. Level 2 can get you 3 to 4 marks. Level 3 can get you the highest marks, 5 to 6. And in the level 3, you need to have explained why you include the 100 ohm resistor. So I've done that. And I'm tackling this question as if we're going for the highest amount of marks possible. Don't forget that in part A the mark scheme was incorrect. The mark scheme is also incorrect here when it talks about possible voltage ranges for the circuits and the action of the circuit. So bear that in mind if you're using the mark scheme, that the values there are incorrect. So if you're scratching your head wondering where certain values came from, it's because this mark scheme is for a different question, it appears to me. So let's think about which circuit should we use. We should use, with this one, if we put our 100 ohm resistor in series with our LED between here and then put the suitable meters in, which are obviously going to be an ammeter and a voltmeter, then the possible resistance change we can get here would be from taking this 10 ohm resistor down to 0, the variable resistor, meaning we've still got 100 ohms in series with our LED, and then taking it up to 10 ohms, giving us 110 ohms in series with our LED. So that's a small change in resistance, which will mean that the voltage change across the LED will be small. Now what I'm going to do here is I'm going to assume that the resistance of the LED is close to the value that we calculated in part A, which, if you remember, was 37.5 or 38. So I'll take it as 35 ohms. Let's say that the LED has resistance of 35. Before I draw the circuit, I'm going to work out the potential range of voltages that you can get across the LED in circuit A. With circuit A, the max voltage range across the LED. If the variable resistor was at 0, then it would be 135 in series. So we've got 100 ohms and 35 ohms in series. That means that we would get 1.6 volts across the LED. I've used the potential divider equation to work that out because you've essentially just got 2 resistors there that we're interested in. And if we wanted to do it, so let's say this is the variable resistor equals 0. For the variable resistor equal to 10 ohms, then we'd have 110 ohms and 35 ohm resistors in series. That would give us 1.4 volts across the LED. So we've got a total change of about 0.2 volts. So that's a small voltage change. Small voltage change across LED of 0.2 volts. Okay, now what if we used the other circuit? In this circuit, we could potentially have 10 ohms in parallel with our arrangement or 0 ohms in parallel with it. That gives us a total voltage change across AB of 6 volts, because it would go from 6 volts with the 10 ohm there and 0 with when the slider was on this side of the resistor. The resistance of the LED is 35 ohms. If we had 6 volts across the arrangements, so for in circuit, what I've done here is I've explained the action of circuit A by looking at what the range of voltages across the LED is. I'm going to do exactly the same thing with circuit B. Max voltage range across LED. 0 volts, which is when the slider is there, because you've just got a connection here, so you'll have 0 potential difference drop here. The current is going to flow through here rather than around your circuit here. The total potential difference of the battery will be across this resistor. 0 volts, and with the slider set to on this side of the 10 ohm resistor, with slider set to include 10 ohm resistor. I'll show you how I use the potential divider equation here. The voltage output across the LED would be the total voltage multiplied, which is 6 volts, would be multiplied by the resistance of the LED divided by the total resistance, which is the 100 ohm resistor plus my LED, that's 135. That gives me 1.6 volts. So the total range, a larger voltage range of 1.6 volts. That's bigger than the 0.2 volts that I got up here. So this gives me the better voltage range. This therefore is the circuit to choose. So I now draw my arrangement on here. The positive terminal was here, so the current will flow this way through, so I need to get the polarity right. And the meters I need to put in as well. And that's the circuit I need. So where do we get marks? We get one down here, one here for explaining that action and the voltage range you could get, and one over here for doing the same thing for circuit B. On the diagram, we're using the right circuit, and we've got the LED the right way around, correct symbols used, and the voltmeter and ammeter are the right way, are arranged correctly with the ammeter in series, voltmeter in parallel. So that one gives us 3 marks there at least. The question is 6 marks, so we've easily got 3 marks in the explanation, 3 marks in the diagram. Right, there we go. Anyway, that's question 4.